Hi, welcome back. And today we are going to discuss about per unit impedance diagram. So this is a quick recall about the building blocks. So here already we discussed about the power system, various power system components like a generator, transformer, transmission line, and the various types of static loads or motors, etc. And the system representation of the various power system components for generator, transformer, and transmission line load, etc. So this is a single line diagram. It can be represented by using the symbol, and so in order to determine the per unit quantities, so that we can able to normalize all the different value into the equal to the base value. With refer to the base value. So what is a per unit impedance diagram? So here the per unit impedance diagram, which is used to represent the power system component like the generator, transformer, transmission line, loads, etc. So here we have to indicate their impedance, which is normalized to the base value. Here we have to assume the base value or the base value which is given. We have to choose this is this base value is common for the entire power system. So the base value which is used to simplify the complex calculations by eliminating the different voltage level across the transformer, generator, loads, etc. So here at the time of doing the empathy, so many of them asking why we have to convert the actual value into the per unit value. So it seems it is an extra work. And so actually it is to handle the multi-voltage system without any confusions, so that we can simply analyze the fault system, and we can able to analyze what are the different types of fault which are occurred in the power system. So here just we can see this figure. So the figure, it consists of two generator G1, G2, and almost four transformer 1, transformer 2, transformer 3, and transformer 4, and one motor which is indicated as M. And there are how many bus bars? One here bus bars will be there, and there are two static loads. There is nothing but S1 and S2. So for all the generator, motor, transformer, they are giving some parameters. That is nothing but an MVA rating and KV rating. So also they are giving the reactance in terms of percentage. So in the defined stage, so we have to analyze why the multi-voltage power system, it contains actual value. So why we have to convert into per unit value. So it is an extra work, and we have to do in complexity. So here the main objective, the transformer ratio, it gives complicate while solving the problems, or it gives the complex to analyze the fault analysis. So here we have to convert all the electrical component into the per unit system. So here in the idea exchange, what is the main key concept? So the first point, we have to choose the base value. Here we have to choose the base value. So the base value nothing but new base KV as well as new base MVA. Okay, we have to choose for the entire system. So the MVA, new base MVA is common for the entire system, and the voltage it changes at a different parameter. Okay, and second one, after choosing the base value at the second stage, so we have to calculate the base impedance. So this is a formula. In order to calculate the base impedance, which is equal to base voltage divided by the base apparent power. That is nothing but base kV whole square divided by base MVA. So it can be calculated for each voltage level. So after calculating the base impedance, then we have to convert the power system component into the per unit impedance. So the main formula to calculate the new per unit impedance is equal to the actual impedance divided by base impedance. So the base actual impedance will be given, and from the second step we are are calculating the base impedance. So by substituting here, we can able to get the new per unit impedance. So based on the per unit impedance of the generator, transformer, transmission line and load, so that we can able to draw the simplified impedance diagram. So the impedance diagram, it consists of both resistance as well as reactance. So this is a step-by-step conversion process. For generator, the rated MVA is given and the kV rating is given and the percentage of reactance or impedance is given. So here the percentage of impedance is converted into per unit, which by using divided by multiplying divided by 100, by dividing the number as 100. And if it is needed, you can change the base value also. And for transformer, the rated MVA and percentage of kV, that's the percentage of impedance, and the kilovolt is given. So account for voltage transformation. So here we have to calculate the change in base kV, if it is needed. And for transmission line, so in order to determine the per unit reactance or per unit impedance, the actual value divided by base value. So here we have to calculate the base value by using the formula. And for load, we have to convert the given megawatt or megavolt ampere hour into per unit value, that is per unit reactance or impedance, and we can express as impedance if it is needed. These are the steps which is used to convert from the given value to the per unit value. So here these are the base quantity relationship for power base, voltage base, current base and impedance base. So mainly we are always focusing on the impedance base. So the formula to calculate the impedance base is equal to kV, the kV square divided by base MVA. Base kV square divided by base MVA. So now you can see this is an image, this is a single line diagram. It consists of generator and this is a bus bar. These two are the circuit breaker. So mainly we have to focus on generator, transformer 1, transmission line, transformer 2, and this is nothing but a load. So here all the generator, transformer 1, transmission line, transformer 2, load. So it should be converted into the equivalent circuit parameter. So from this equivalent circuit parameter, it consists of both resistance as well as reactance. Okay, so this first one is nothing but, and this is an impedance diagram of the given single line diagram. Okay, so at the time of the prototype or the executing, so here these are the steps mainly we are focusing. So we have to create and assemble the system. It may consist of generator, transformer, transmission line, loads, etc. So that we have to apply the conversion, we have to calculate the new per unit impedance, and we have to draw the impedance diagram, and we have to compare the fault calculations and as well as the actual impedances. So these are the real-time applications mainly which are used for the fault analysis, like the short circuit fault or open circuit fault or line-to-line fault, that may be a symmetrical or unsymmetrical fault. So for the fault calculation, it is very easy. And for the relay coordination, if any fault is occurred, immediately we have to protect our generator, transformer, bus bars, etc. So here this kind of impedance diagram which is used to coordinate with the relay. And for the load flow studies, it can be used to interconnect the various power system network. And for the analyzing the stability, whether the power system is in a stable condition or unstable, so because of under disturbance, it may be an internal, external, and external. So we can, with the help of this impedance diagram, we can able to analyze the stability analysis. Okay, so what is the advantage? Why we have to use per unit? So that we can eliminate the different voltage level across the power system. So we can able to simplify the calculations, which is very easy, which is almost 0 to 1 with respect to the per unit value. And it can be done for universal comparison regardless of any kind of rating or value, etc. And the manufacturer data. So the equipment often specified per unit value or in terms of n percentage. So this is a mind map or per unit impedance diagram. So at the fundamental stage, so we have to calculate the base quantity and normalizing the concept, and we have to consider the voltage level. At the time of conversion process, so the generator impedance has to be calculated, and a transformer impedance has to be calculated, line impedance has to be calculated, and load representations. And application can be used for fault analysis, load flow, stability study, and the production of the entire power system. So this is a curiosity challenge. What happened to per unit impedance when a power system is expanded with a new voltage level? How do engineers maintain the consistency throughout the grade? So if you know the answer, you can put in the comment section. So this is an assessment question. Why is per unit representation prepared over ohmic value or the different resistive value in multi-voltage power system analysis? So these are the few references for this topic. Thank you.